Let's solve some problems involving time to failure based approach to the reliability function. Let's take a minute to read the problem, and then we will solve it step by step. So let's define the random variable capital T as the time to failure exponential distributed with a mean of 2000 hours. The exponential random variable has a CDF which looks like this, where the mean mu is the required parameter. Okay, so what's asked for is to compute the CDF at a certain time. So let's find small t first, and 1.8 hours a day over a year, which is the design period, which is the warranty period, and then so that comes to about 657 hours. So the fraction of twos that will fail during the warranty period, the fraction of display units, is the CDF of capital T evaluated at that particular time instant, which is 657 hours. So if we just plug in the values, it comes to 0.28. So 28% of all such display units would be expected to fail before the end of the warranty period. The next problem that we will look at starts with the CDF of the time to failure of a certain component. So it's given as you see on the screen, and we need to find out the design life such that it never falls below 90%. So if you'd like to solve it, please pause the video, otherwise I'll present the solution step by step. By definition, the reliability function is 1 minus the CDF of the time to failure, and we need to find the minimum time t star such that r at t star is at least 0.9. So it now becomes a simple solution of t star from a one variable equation. So we end up with a quadratic equation in t star, and because t is only non-negative, the time to failure is defined only for non-negative values. So the answer is 1.91 units of time. So that is the time up to which the reliability is always greater than or equal to 0.9. So beyond 1.9 units of time, the reliability is going to fall below the specified 90%. The next problem we look at again starts with the definition of the density function of the random time to failure. So our starting point is the PDF, and we need to find out 4 answers. So let's take a minute to read the problem, and then we will take up the solution. So first we find the reliability function of the appliance. Let's start with finding the CDF. which is the integration of the density function, and we integrate the density function, which is defined over the entire line from 0 to infinity. So x is the dummy variable, and we integrate that, and we obtain the answer as 1 minus 16 over t plus 4 whole squared. So that's for all non-negative values of t. So that is the CDF of the time to failure, and we know that the reliability function is 1 minus the CDF. So the reliability function is 16 over t plus 4 whole squared, as you see on the screen. So the next two parts, part C and D, asks us to find the mean time to failure and the mean residual life at the design life, which is we have to find next. So the design life, as we did in the previous problem, is that point in time at which the reliability equals 0.8. So we need to solve for t star, and the answer is about 0.47. So that's the only feasible solution from that quadratic equation. So at 0.47, we will find out the mean residual life, but let's first find the mean time to failure, so the unconditional mean. So that would be, by definition, we'll use the area under the reliability curve. That's convenient, and if we complete the integration, we get an answer of 4 units of time. Now let's plug in these quantities in the definition of the mean residual life. So the mean residual life integrates the reliability function to the right of t star and normalizes by the reliability at t star, so which is by definition 0.8. So if we complete the integration, we get an answer which is 4.47. So it's interesting to note that the mean residual life at the design life is greater than the original mean time to failure, and that might appear surprising, but it's a particular kind of component that we will find out in the next lecture has what is known as a decreasing failure rate. So components that exhibit such kind of property would have the mean residual life, like you see here, which is a little larger than the unconditional mean life.